Yeah, my name is Ron, and I'm in Denver, Colorado. And I want to thank Elizabeth for inviting me. It's cool that this organization, this group gets together. Um, it's nice to have an afternoon break, though. For me, it's 7 in the morning, which is fine. I'm a morning person anyway. Um, so yeah, happy to be here. Happy to talk a bit about AI and how it might relate to birding and other wildlife biology pursuits and things like that. Maybe do a little bit explaining of what it's doing. Um, I have only a handful of slides. There's two ways to do this, right? Talk about it and keep it fun and light and hope there's questions and discussion, which is what I'm hoping to accomplish, or just, death by PowerPoint and give you guys 100 slides, one after another with equations and charts and everything. I do have one figure, but it's only one, so not too bad. Excuse me. So if there are any questions or anything like that, like I said, just feel free to ask. So this is the book. Why even write a book on birding and AI? So there is a story to this book, and it starts during lockdown, like last week's speaker. So, as everyone was locked down and not able to go around where they wanted to usually go during the pandemic, I started walking and I started going out in nature a lot more than I usually do. Computer people aren't known for that. And I noticed, especially in Colorado, it's one of the best places in the U.S. for birding. There's just tons of birds everywhere. I had been introduced to birding decades ago and just didn't get into it. I had young children, didn't have time for it, and all those sorts of things. But when I realized there were apps out there now, like Merlin, actually I thought I was going to make my own, and then I found Merlin. I thought, okay, two things I'm fascinated with now. I'm fascinated with all the birds and variety of birds that are always around us and we never notice. My brother lives in Florida, and I went walking with him and was pointing out all the birds, and he's like, I walk this way all the time and I never notice any birds here. So he's like, can't believe there's so many here. I started slowly getting into it. And as I was walking, I would walk the same paths, a nature preserve near my house and a lake near my house. And I thought, as I do this, I sit and I muse, and I'm having all sorts of thoughts about different things related to birding and natural world. I thought, I could write some essays about this. So, as mentioned, I do write books. Normally, I don't call myself a writer, though. I'm an explainer, meaning I'm not a wordsmith. I don't write, great things, great literature, or anything like that. So I thought I would try that. So I went looking for publishers and talking to different publishers about the idea of a book about essays related to bird walks. And so I contacted Pelagic, and many publishers, if you've tried publishing, you just get silence. They were interested in talking, and they came back and said, well, there's actually a lot of books like that, but we see about artificial intelligence. There are no books about artificial intelligence and birding, and that's a big thing now. Would you be interested in trying to write something like that? So I said, sure. I jumped at it, and that's where the book came from. So what I did was and I was doing this already, but I spent about 2.5 years collecting images, and every image you see in the slides here is a picture I've taken. I don't use a professional camera. It's a bridge camera. And it's all taken from basically these two areas that I use in the book. Some of the pictures were used in the book, and some, are just more recent and things like that, though I think most were used in the book. And so I threw them in here because that way we have bird pictures and not lots of, like I said, diagrams and figures and things. So most of you will recognize the European starling on the left. They are very common now in the U.S. As I understand it, about 100 were released into Central Park in New York City in the late 19th century. And current estimates are there's between 150 million to 200 million, I think just in the continental US alone. So they're all over the place now. So this starling was nosing around in this nest on the tree that was almost certainly made by a northern flicker, which is the bird on the right. It's a kind of woodpecker, also extremely common in my area. So that's our bird picture for there. But yeah, this is a great time because of AI to get into birding, and I think most people know that. You know, the Merlin app, I think, has maybe 10 million users, half that maybe, worldwide. I see a lot of people using it when I'm walking around. I have people with their phones out, and I'm like, Merlin? They're like, yep, using Merlin. So it's been a huge boon, not just to get people interested in the natural world, but of course, for researchers to collect all that data and things like that. And so, yeah, artificial intelligence is what lets you do that. But let's understand a little bit more maybe about how it's working. I see a question in the chat. Is there a question in the chat? I don't see it. Okay. So let's spend a few minutes talking about AI at its core. This is our one figure, and that's a great horned owl. I figured, owls are a symbol of wisdom and knowledge, so let's learn something about AI. So I threw a bunch of terms up there, and we can talk about each of those. Those are fundamental terms, and maybe they're familiar to people already. But AI itself is not really new. It's new and it's not new. So it was actually a term coined right around mid-1950s. There was a famous Dartmouth AI conference where, computer science names that became legends got together, and they figured, we're going to get this done. We're going to figure out how to make machines intelligent. It'll take us maybe a decade. And of course, it didn't take a decade. It took a lot longer. And there's reasons for that. One reason for that is there are two ways to think about trying to make a machine intelligent. One way, and this is called symbolic AI, is the way that was used from the 1950s all the way up until early 2000s. And it was, okay, well, we're fairly logical creatures, therefore intelligence must be logical applications of scripts of how you do things, algorithms, logical sequences, and they just went wholeheartedly into that. It doesn't work. The best they got were known as expert systems in the 80s. They still exist. They're called rule-based systems now. And they're just basically huge collections of if-then statements. So if this is true and that's not true, or this is on and this is off, then do this. And you can capture useful knowledge that way. And there used to be a career called knowledge engineer that, they would interview experts in a particular field, say, physician, and try and capture all the nuance of what they do to create the rule set that mimics what they do. And there were some successes, but it's very brittle, and you can't add new knowledge, and it certainly has no relevance to how biology created intelligence, right? So the other way of looking at it, and this came early on, even in the 1950s, it's called connectionism. That's kind of an older term. And it was basically, well, let's think about what brains do. They have very simple, basic components that get connected together in vastly complex ways. And from that, intelligence emerges. And that's a word I'll probably use a lot, emergence, because that's the core of what's going on with this stuff. So the guy behind that was Frank Rosenblatt, and he actually had a machine called a perceptron, Mark I perceptron. In the 1957, he demonstrated it to the U.S. military, and it was able to actually interpret images, very crudely digitized, I think 20 pixel by 20 pixel images. And it did certain things, and it was, somewhat useful. And it was all mechanical, doing what I'll describe that we do now with modern networks, at least certain kinds of modern networks. But he made bold claims. He said, oh, this machine will become conscious. It will be able to talk to people. It'll be able to translate languages. It'll do all sorts of things. And of course it didn't. And some researchers found a flaw in how he had built the networks. And it's related to that H function I'll talk about in a bit. And so that people just abandoned neural networks. They thought they were nothing useful. And that didn't last. That lasted until well into the 80s. In fact, in 1987, I had an artificial intelligence class as an undergraduate, and I remember the professor saying certain things. So in 1987, he said, eventually a computer would beat the world's best chess player because there's an algorithm for playing chess, and it was known. And it was just a matter of scaling up the computer to be able to do that well enough to beat a human being. And he said no one would ever make a computer to beat the world's best Go player because there's no algorithm for that. And he also, he also said that neural networks were toys and they would amount to nothing. And he was right on the first part and wrong on the second part. So in 1987, a computer did beat the world's best chess player using that sort of algorithm, plus a lot of other things. In 2017, a computer beat the world's best Go player, and that was big news. Maybe it was 2016. I think it was 2017. And of course, everything we use now that we call artificial intelligence is a neural network. So he was wrong about that. So there was a lot of bias that kind of held AI back, but there was also a real practical reason for it, which is computers weren't up to the task. There wasn't enough data for training. There wasn't enough computing power to actually build networks big enough to do anything interesting. And that all started to change in the early 2000s. So it was kind of a confluence of things that let us get to where we are now, let neural networks actually become useful. So the thing that Frank Rosenblatt, who never lived to see it, he died in 1970, figured would eventually happen. So let's look at these terms a little bit here. So model is a generic term for any AI system, anything that takes inputs and gives you some kind of output. So input would be, in this case, a picture of a great horned owl. The output would be something that indicates great horned owl as a label. But, it can be other things. It could be a different kind of image. It could be a collection of not just this is an owl most likely, but also this is where it probably is in the image. We'll look at some of that later. Neural networks. So everything I'm talking about AI now is neural networks. There are other things, but that's all I'm talking about. Data set is, data sets are. But data sets are the key to neural networks. So what you're trying to do is take a blank slate and have enough data that you can condition that model to predict, this is called supervised training, predict from unknown inputs a meaningful output. So you might have all sorts of, say hundreds of images of great horned owls, and they're great horned owls, so you label them as great horned owls. Usually the label is just an integer in a list. And you use those to condition the model, and I'll talk about what that means in a second. And that's training of the model. And once you've conditioned it, you can test it by giving it things it's never seen. Say, okay, what do you think this is? And it'll tell you it's great horned owl, or maybe it tells you it's northern flicker. It'll make mistakes, and you can characterize that. And you can go back and forth iterating until you get a model that works well with what you want. Inference is just using the model, right? So you're training it for some purpose. So now you have a model. Now you put it on a phone app, call it Merlin. So people can put pictures in there, and it can come back and tell you what bird is in the picture. The way that I think about this is especially for the data set, and I'll talk about this a little bit more in the next slide, but you're dealing with interpolation and extrapolation. So what you want is a data set that can capture the essentials of everything it might see when it's used in the mind. So an example might be, you want to have a model that can predict, let's say, great horned owls from images of other things. So your data set, you say, okay, I have all these pictures of the owls. I have all sorts of pictures of trees and bushes, and I'm in a model. And I know which are owls, and I know which are trees and bushes. So if I do that, I can make a model that's going to look wonderful, right? Take the data I've held back for testing and put it through there, and it's going to say, yep, owls, trees, perfect, it's great. So then I take it outside, and in flies it wouldn't even have to be like a barn owl. It could be a robin, and it will tell you that that's a great owl, which of course it isn't, because you didn't have data in your data set for that case. So you have to be as encompassing in your data set as possible. So what is then the neural network? So that's this diagram down there. So this is a particular node. This is a node. This is the fundamental element of all neural networks. Everything from what Merlin is doing up to what ChatGPT does. And all it is a collection of inputs. So that's the X0, X1, X2, they're numbers. Neural networks only work with numbers. And each of those connections is a weight, W0, W1, W2. And then there is additional value called the bias, that's the B. So what happens is the node says, okay, I have a certain number of inputs here, 3. I'm going to multiply X0 by W1, and then I'm going to multiply X1 by W1, 0 rather, W1. I'm going to multiply X2 by W2. I'm going to add those products together. I'm going to add B. I'm going to use that as an argument for what's called the activation function, that's H. And whatever value that gives me, that's the output of the node. Modern activation function is really simple. It just says, is this sum greater than 0? If so, output the sum. Otherwise, output 0. That's called a rectified linear limit, and that's the one that most models use. And that simple operation, when you connect everything together, multiple layers, and with some fancier layers in there as well, depending on what you're doing, that's the core of everything. So when you hear people talk about training, or they'll talk about how big a model is, they're usually talking about the number of weights and bias values, because those are the magic numbers. The structure you use, the way you orient the layers of the nodes and connect them together, that's the architecture. But the architecture is a blank slate, and it's training that finds the weights and biases, and it does it through a gradient descent sort of application. So it's using calculus to find those and iteratively update them again and again and again. And what it really boils down to is multiplying matrices by vectors. Represent these layers of these as matrices and vectors. So the faster you can do that, the faster you can train. The larger you can make that collection of matrices and vectors that are multiplied by them, bigger your model can be. And then, of course, there's all sorts of tricks and different ways of adding different layers and things. But that's the core of everything that these models do. So, and again, if there are any questions, please ask questions. But I have the word emerges here because to me that's how it works. So why can ChatGPT do what it does? And nobody expected it to be able to do what it does. I want to know who the first person was who asked an early version of this transformer. The architecture is called transformer. Who asked a transformer architecture a question and got an intelligent answer. They probably freaked out because that wasn't the goal. The goal really was to predict meaningful, coherent text given some initial prompt. And the fact that core transformer architecture was developed for language translation. It came out of Google in 2017. And so they didn't even have an idea of what it could do. So that's why I say so that's why I say the model emerges from the training process. I think of it, there's that old Kevin Costner movie about Field of Dreams, right? So the mantra was, if you build it, they will come. Meaning if he builds this stadium and, this baseball field in the middle of nowhere, the ghosts of these players who were behind will show up and play. So I think of it a little bit that way. So the architecture, the transformer architecture, by accident, for the most part, created an environment where seemingly intelligent behavior could emerge if trained on enough data. And the training data for something like ChatGPT is unlabeled. It's self-labeled in a sense. Right? If you want to train what Merlin does for pictures, you need collections of different bird pictures, and you need to know what those birds are. The way ChatGPT was trained initially on text, it's now more complex with imagery. It would take a phrase like Mary had a little lamb, and they would drop the word lamb. They would say Mary had a, and it would predict for all its possible outputs. The outputs are not really words, they're parts of words. And if it didn't predict lamb, it would get penalized. And that's during gradient descent process. Just do that on literally almost the whole internet. And that's what ChatGPT originally became. That all sorts of behaviors emerged from that. And think of it, in order to be good at predicting the next token, the next word that you want to output, some representation of intelligence has to be there. You have to have some idea of the world and how it works and things like that. So it's a happy accident. We'll paint with Bob Ross. But it's still at its core, it's these fundamental base set of units working together. Questions? So that was more than 2 minutes. So as I mentioned, data is everything. So these images represent an example from the book where I built a data set. So these are 6 different birds that I have many pictures of. There's places I would go. And again, I said I was using a bridge cameras, not professional quality. But I had, anywhere from 100 to several dozens, which isn't a lot of data. And I used them to build a data set. This is a data set used in several chapters in the book. And the goal is, okay, can we build a model that takes these 6 birds and can differentiate between them? And when you build data sets, our usual approach, of course, is collect lots of labeled data. So all these images, hundreds of images that we know the labels of, and then we split them into 2, at minimum 2, often 3 groups. So that's what train, validation, and test are. So train is used to actually update the weights and biases of the model. And only training does that. Validation and test are kind of the same thing, but you use validation while you build the model. So you pick an architecture, and here we're talking about models. I'll do it in the next slide. We'll talk in more detail about it. You pick your architecture, you use your training set, run until you think you're good, which means the model is getting better and better and better at predicting and making fewer errors. And because you're using gradient descent, it will actually always get better and better unless something is catastrophically wrong. So you can't really take what the output is on the training set to make yourself think you've got a good model. You have to give it things it hasn't seen during training. And that's what the validation and test sets are. So the validation set is used during training. Okay, so if you pick an architecture, you start training, you realize your validation set is never getting accurate. It's never learning well enough to do the validation set. So you might stop, might change your architecture, go back and iterate again. So you take train and validation to iterate until you build a model. When you're finally done, think, okay, this is a good model, this is good enough for what I want to do. Then you take the test set that you've never used for anything else, and you put that through the model, and that's what you use to determine the quality of the model, how many mistakes it made, what classes, I mean, which bird type did it get, which did it get wrong, which did it get right, and stuff. And it's really important to do that. Never report your train or validation. You see this in a document or in a talk. I literally saw someone laughed on stage for doing it. It's always the held out test. But again, since data is everything, you have to make sure the data you're showing it is relevant to what it'll see, right? So I build this model with these 6 different bird types, and I hand it an ostrich picture. It will always make a choice for one thing. So the naive model can't say, well, I don't know that, but it's none of these 6. There's ways to try to do it. So it will give you a probability, really, because it's producing probabilities. So it will give you a probability for each of these birds, and you just take the highest one, and that's how you decide your label. So it has also learned, though, things about birds with long necks, birds with long legs, birds with short legs. So if you take this model and give it an ostrich, it might come back with a great comparison as the highest. So it will be somewhat right, but it's not going to do anything you want it to do. You think you're going to see ostriches in the model when they deploy it, have ostriches in there, and you're going to say, this is not any of the birds I'm interested in. Another way to think about data is how to think about it. Is your data set, is a sample from some sort of data generating distribution. So think platonic ideas. There's some distribution that creates the data of the kind you're interested in. You have a sample from that distribution, and you want to use that kind of as a representation of the entire distribution. So you have to make sure you've got enough data to cover that distribution well. And again, so matches things that your model would see when you actually use it. Another way to think about it is, you can approximate the probability distribution using histogram. The more data you have, the closer that approximation is to the probability distribution. So that's another way to think about it. So get as much data as you can. You never have too much data. Sometimes when I'm working on things, people say, well, how much data do you need? My answer is always the same, all of it. As much as you can get. Questions? No, I don't leave time for questions. Hopefully discussion, right? Because there's always controversy with this stuff. So traditional computer vision, when you're dealing with bird images, that's computer vision, looking at pictures. This is almost certainly what Merlin does. We use what are known as convolutional neural networks. So they're still neural networks, still have those nodes. They use a convolution operation. So if you're familiar with digital image processing, it's a way of sliding a smaller matrix over a larger matrix in this context. It has a formal math definition, but in terms of computer vision, that's what it's doing. And with that, you can extract edges of a certain orientation, talk about textures, you can get colors, if it's RGB. So what it can do is it can tell you how the image responds to those particular filters. And in the late 90s, Yamakun, he recently left Meta, and his lab created these convolutional neural networks. And they did it actually as a way of simplifying models, so you have to learn fewer parameters. And it just opened the floodgates of computer vision. So prior to that, it was always frustrating, right? We glance at these images, in this case, a kestrel, we see kestrels. Why can't the computer see kestrels? Well, of course, the computer couldn't see kestrels on its own, but with a convolutional network, what the computer could be trained to do in the neural network is learn a set of convolutional filters that transform this complex input image into a vector. So I call them embedding vectors. It's just a vector in a very high dimensional space, say 1,000 dimensions. That is a new representation of that image. And it's one that responds in ways we can't really understand, but it responds in ways that make the essence of what's in the image easier to discern. So the top level part of a convolutional neural network is really an old-fashioned neural network by the 1980s. And because you performed this transformation between all the complexities of the input image and the final vector representation, the simple model can decide between them. And in fact, at first, when I first started working with this stuff, we didn't even use neural networks. It's the top level models. But if we learn them all together, that works better. So that's the essence of what it's doing, and that started in 2012. Because there was a contest, computer vision contest called ImageNet, 1,000 different classes, and accuracies were just terrible. Not for lack of try, but in 2012, when it was Jeff Hinton, Alex Wachowski, and someone else used a convolutional neural network that was actually a fairly complex one, they had like a 30% jump in accuracy, which was just unbelievable. So that really started the deep learning revolution. And deep learning is just neural networks with many layers. Because in the past, you could be trained, 2 or 3 layers. But they also, with compound, hundreds of layers. So in the traditional way, take the training set, train a model, think it's ready, test it, put it out in the wild for inference. So somebody using Berman on their phone takes the picture at the bottom, doesn't know what it is, model comes back and says it's a customer. And that works really well. But that's not ChatGPT, and that's not second revolution. So this, to me, this is the first deep learning revolution that happened in 20. It was very exciting. I've heard a lot of conferences, and just you would go to a conference 3 months after the previous one, just be like blown away by what was happening. Of course, none of us were prepared for ChatGPT. Questions? So, question: what about 3D data? You take the large 3D as a small thing. It's tricky, and people have worked, of course, on that for a long time. I think if you're careful, and it depends what you mean by a dirty data set. The larger dirty data set might be preferable, because a small one is not likely to cover all the scenarios that you're going to encounter, right? Especially, if you're interested in wildlife, that's right. You put a rail cable out there, who knows what's going to show up, right? So you need a lot of quotations, you need a lot of writing things, and types like that. And with this, so for this whole talk, I'm talking about images of, as we'll learn audio that you turned into images. So it's not something like I have a spreadsheet and there might be missing values. That's not really where you deep neural networks actually generally provide that. There are other models, random forest, decision tree, stuff. Like when you hear companies are scooping up the whole internet, it's not true. That trade on the best. That it's dirty data. So that images, the dirty part might be the labels of what certain fraction of what was wrong. I've played around with that to tolerate 5%. Now it depends how accurate you need to be, but label error and tolerate. So yeah, the core of traditional computer vision is taking the image, turning it into a new representation that simple computer model understand. Books I have the example digits. Digits are simple, especially for us. But when you look at the vector, it's a decision about which you get it. It wouldn't take too long to learn what kind of notes you said. You're very consistent. They're not identical, but they're consistent. So how do you do computer vision? Generally, so generally, dependency. That's all sort of. What else? Before there, so about this somehow if you're starting, especially the new project, don't necessarily start from scratch. Instead, we would want to build on web. So we might do the foundation. So those are models that we trained on vast amounts of time. So OpenAI trained the model that there are what they did there is they took billions of images, text associated with trained the model not to produce the labels, but to produce the better images. So in this example, the text that's literally flips out goes on. This is the thing that's important is that the text and images are similar concepts. That's associated images. Those both text and images. Because of that, they're that vector relative kingfisher is going to point sort of in the same direction, large dimensional space, as the vector created by calculation. So in the book, I started out with my simple data set in the old-fashioned way, right? But obviously, it's to prove so somewhere on started to process things. But what happens is good. So say I have an unknown person, say that vacuum. I have a list of all options to mess with our process. That would be fair direction that was pretty all the time. Take them out to
sorry, to interrupt you, but we are having a little bit of trouble that hearing you. The sound is degrading. Is it from your side? Can you try anything to correct that?
I have to use an external mic. Is this any better?
Yeah, that's much better.
I'll talk a little closer to the microphone. Sorry.
Yeah, this is good.
No, that's good. It's all good. So the point is, you take the image vector and you take the common name vectors and you find which ones point almost in the same direction, which have the smallest angle between them. And if you do that, you're going to be instantly in the 95% accuracy range, even though you haven't trained anything, because OpenAI has already done the work for you. So those vectors encode a lot of concepts. What the concepts are, who knows? Humans can't understand what's in those concepts, but they're very consistent. And if you give many images of that kingfisher, you're still going to end up most of the time being closest to the embedding of the text phrase belted kingfisher. And so all the sparrow images here, that was a test from the book, and I only had handfuls. That's the other advantage. When you do this, you don't need large data sets anymore. You can get away with much smaller data sets because the clip embeddings have so much buried in them. Even if we don't know what it is, it's meaning buried inside them that you don't need a lot of data. So I took images, just a handful of images of each of these 9 different sparrow types, and even that was 78% accurate. If you hear banging at the door, that's my son's dog, who apparently hasn't read the note that says I'm in a meeting. She'll wander away soon. So that would be a recommendation if you want to start a new project. I would start looking at what you can get from something like Clip or OpenClip. And that way you can get away with a lot less training data. But it's also impressive because this is a similar sort of thing that's happening inside of a language model like ChatGPT. There are many layers of these embedding vectors, and they get manipulated in different ways. But there's still concepts being learned in a way that people can't really understand. Anthropic has done some interesting work trying to tease out concepts that their models have learned, even disturbingly going so far as injecting concepts and then asking the model questions unrelated to those concepts, only for the model to complain that it's having trouble answering the question because it keeps thinking about, I think it was pineapples or something, owls. It keeps thinking about owls, and it doesn't know why. And it's because they were injecting information related to embeddings of owls. So they're kind of messing with its mind. All right, I think there's a question here. Okay. Yeah, let me know if the audio is fading again here. I think I only have maybe 2 more slides.
Yeah, I think it's okay now.
Okay. Yeah, 2 more real slides. So everything I talked about was, give an image, what bird is in the image. Of course, there might be many birds in the image. So people want to do other things to localize. So that's detection. And there's different levels of detection, and I talk about this in the book. So on the left, we have bounding boxes, and everybody has seen these by now. This is from a model called YOLO. You only look once. It's very fast, but if you just download it as is, it only knows something like 64 different categories. So it says, oh, those are all birds. Bird, 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 bird. Sometimes it detects them twice, as you can see on the bottom one. Sometimes it misses at the top. But it's a very rapid way of doing it. And so what the model is doing is, I think YOLO does it just by partitioning into different cells and using a probability of things being in one place or another and then shrinking the boxes. But it's producing a probability over possible labels, the highest of which is bird in this case, and coordinates of a bounding box surrounding what it thinks are the pixels of the bird. And of course, that's super useful. It's also super fast. But, it called all the birds birds. But it did tell you where they are, right? It told you the bounding boxes. You can go one step further, and that's the upper right, to do semantic segmentation. And this is done a lot with medical images, perhaps, of histology slides and things, where you get a label assignment for every pixel. Now, this is a simulation that I made. So in that sense, you would get every pixel belonging to each bird, but they're all still labeled bird. So if they're disjoint, you could count them and things like that. Then one step further is instance segmentation. So you get all the pixels of all the birds and they're differentiated one from the other. So you know how many, these pixels belong to this bird, not just all generic bird pixels. And so detection is of course, very important. In the book, I don't experiment with it too much. I do it in a very simple way, old school way, using the clip embeddings, and that works. I just didn't put any slides here because the models are too complex to train easily without additional hardware and things like that. And I wanted the models in the book to be trainable without even a GPU. In fact, I didn't use a GPU to train them. But that's the next step beyond what is it, where is it? Okay, there's a question here. Okay, that hasn't cleared yet. And I do want to leave time for possible discussion. So Merlin classifies audio also. So how do you do that? Well, there's multiple ways, but I think the best way to do it, and the way I do it in the book, and the way I haven't asked, but I'm sure Merlin is doing, is to take the audio and turn it into a picture. So on the right here, I have 4 sonograms. In other contexts, they're called spectrograms. And on the x-axis, you have time, and on the y-axis, you have frequency. And then the intensity at that frequency is whether it's, in this case, darker or lighter. Of course, you can change the color tables and things like that. The models actually don't seem to care what color table you use. They learn regardless, as long as you're consistent with the color table. And what you're doing is you're taking, say 100 milliseconds of audio, doing a Fourier transform on it, calculating the power in each frequency, and that's what you plot going up vertically as you sweep across in time. And of course, I think most people here have seen these, right? You have the blue grosbeak there. It's got a particular shape to, whatever call it was doing. Great horned owl, like many owls, have low frequency hoots, so you see those as the dark bands way near the bottom of near the x-axis, and so on. So you could teach yourself to tell the difference between these. So if you can do it, then a model can probably do it too. And again, I think that's what Merlin is doing. And so I do that example in the book as well. On the left, the example there is, can you make a model to learn the difference between Canada geese, and this is audio again, Canada geese and cackling geese. So the left has a Canada goose, the right there's a cackling goose, and then a snow goose decided to photobomb. But if I do that, I can get high accuracy. So test set accuracy is 94%. MCC is Matthews correlation coefficient. It's a good single number metric. The higher is better, because accuracy is only meaningful if you have the balanced classes, right? So if you had a very rare thing you wanted to see, you could just say, well, it's never that, and therefore my model is now almost 100% accurate because it's rare and it's almost never that. But that's not useful. So you would look at something like the Matthews correlation coefficient. But that's how you would use a convolutional network with audio. You would turn it into an image and then analyze the image there. I'm almost out of time. I want to leave room for questions. So just, where can you go to learn more? Shameful self-promotion. There's 3 of my deep learning books. I have another one that will come out later this year. But you should also look at different things. Coursera used to be free. I guess it's not all free anymore. But this AI for Everyone is free, and it's Andrew Ng, who I think created Coursera, and he's also a well-known deep learning researcher. And the others, I believe, are free as well. So there would be places you could look to kind of get into it at the next level. And I think that's it.